Hi, yeah. Well, you can't start a talk without saying hi. So, hi. Oh, my little sorry, my remote just needed to wake up. My name is Sinjo. In my spare time, I like to post ridiculous selfies on the internet, although owing to the recent downfall of society, they now have less varied backgrounds. And today, I'm going to be talking about rewriting binary logs because your database broke. So for a bit of background, I work as a site reliability engineer, which is kind of like a software engineer, except you end up caring more about systems level stuff, so databases, load balancing, how things actually run in production. And I work for a payments company called GoCardless, and the TLDR of the company is that we are a payments API. Merchants who use us make requests like this. We move money from their customer to them, and everyone's happy. Because of what we do, there's a reasonably high sort of pound or dollar value on each request. Like failing to process payments generally makes people very sad, which is kind of different to if you're running a service like Twitter, where failing to post one tweet is fairly low stakes. So because of this, uptime is really key for us. If our API goes down, our merchants are losing money, and if we do that a ton, then we lose all our merchants. So today I'm going to talk about a time where we kind of failed our merchants, where we had a production outage for a couple of hours. And it was an outage of our primary database, Postgres. It was all the way back in 2017, and we were down for 2 hours across the entire payments platform. And the cause of it was a failure in what we have as a cluster of Postgres instances, which we use to store all important kind of merchant data. The machine running the primary instance failed, and what should have happened is an automatic switch over to one of the replicas. Unfortunately, on that day, for some reason, it didn't happen, and we stayed down until some SREs were able to manually reconfigure things and bring it back up. There were many parts to that investigation, and way too many to fit them all into one talk. So today, I'm going to just talk about one I found, well, personally, the most interesting one of all. So today, we're going to focus on debugging parts of a system that you don't normally touch, and we're going to try and reproduce something that happened with Postgres binary logs during that incident. But first, what is a binary log? When we hear the word logs, we normally think of things like this. These could be web server logs from any popular web server like Nginx, Apache, Lite, or whatever else. The kind of things you might see when someone visits a blog. Databases have a different kind of log. Now, most of us are used to interacting with databases at this level. Let's say we inserted the names of all of tonight's talks into a table. You've probably come across SQL at some point, but at some point the database has to put that down onto a disk, down onto persistent storage, which could be a hard disk, or if you found yourself traveling back in time to 2000, it could be a hard disk if you time travel back to 2005, but nowadays it's probably a solid state drive. And I'm about to give you an explanation that's kind of a simplifying lie, like think A-level physics. But it's close enough to the truth for us to work with in this talk, and it avoids bringing in 2 or 3 more topics. So whenever you run a query that adds or changes data, like insert or update, the first thing the database does is it writes a record of doing that to a log. That is the binary log. So when you say insert into talks values binary logs, the database takes note and goes, OK, I wrote binary logs into the table talks. This happens before updating any of the actual table data or indexes or whatever else. But why does it bother doing that? Well, databases have to survive crashing, right? Like if your database crashed and lost or corrupted your data, you'd be pretty sad. And as I mentioned briefly there, sometimes you have multiple things that you need to update because of one insert. If you're inserting to a table that has an index on it, first you need to put the thing into the table, and then, oops, oh no, Postgres has crashed. What happens now when it comes back up? Your database is in an inconsistent state if this happens, and if you go looking through this index, you will not believe that row 3 exists. So we have binary logs. When Postgres starts up, it can make sure that it got to the end of those logs and go, no, we didn't write into the index. Let's fix that. The other thing that they're useful for is replication. So I kind of mentioned earlier that we have multiple Postgres instances, and the replication of data happens between them. It turns out you can use those same binary logs to propagate data between multiple nodes. So why am I suddenly interested in rewriting them in some way? Well, it turns out that during the investigation of that incident, we ran into a really weird-looking error message on one of those replicas. We saw this invalid record length at some position in the logs, and it was kind of suspicious. And like one of our hypotheses was it this binary log thing, this error message we saw, that meant that the replica wasn't promoted? Maybe the cause of this message was the reason that we stayed down. And in order to test that, we have to be able to repeatedly reproduce this outside of production so that you can understand why it happens and what effect it has on the cluster. So our goal in this talk is to produce this error message. Now, thankfully, we can cheat. Postgres is open source, so we can look at literally every line of source that we're running. But every technique that I'm about to talk about now also works on closed source software, where you don't have documentation about the code or file formats. It's just that we have a special name for that, and that's called reverse engineering. But anyway, let's work with the source. So we can start by checking out the version of Postgres that we were running and using grep to search for that error message. We get 3 hits. The first one gives us actually a really simple conditional that we should be able to trip. So I've highlighted just that here, which is if total len less than size of xlog record, report this error. So really what we want to do is try and make this condition be true. Try and make total len be less than size of xlog record. Well, what the hell are those? We go searching for size of xlog record, we can see that it's a constant. It's the size of some C structure called xlog record, which we don't know what xlog record is, but we don't really care. What we know is that this is a constant value greater than 0. So really what we want to try and do is make total len equal 0 at some point. Now, how can we do that? It turns out total len was a local variable in that first function, and it's read off an xlog record. So what does it look like? If we jump to xlog record, then we can see that total len is a field that says, here is the total length of this record. So we can kind of see how this would all fit together. We've got many pieces, but we need to bring them kind of all into one. So what was that check saying? If we go back to that conditional, it's relatively simple. So what this is saying is that if the record says it is a size that is smaller than the smallest possible record, then obviously that makes no sense, and Postgres should error out. So if you remember those logs I talked about earlier, we need to go and take a look at how those end up on disk. We need to pull them out of Postgres and take sort of inspect them. So if we go back to our boring SQL and we run it against Postgres, and we grab one of those binary log files and we open in a hex editor, we are greeted with a barely comprehensible wall of data. On the left, we have hexadecimal representations of that binary stream, and on the right, we have it translated where possible into standard ASCII text. If you aren't familiar with ASCII text, it's worth having a tiny bit of background on this. This is the simplest way that computers can represent text. Each character has a numeric code assigned to it, and you can see those in whichever number system you want, decimal or hexadecimal. Today, we care about these 2 columns, the hexadecimal representation and the character itself. So if we go back to our barely comprehensible wall of data, there's good news in it. We can see those talks we inserted. That data is there in the stream of writes we made to the database. Presumably, that xl.len field is also in that data. It's just not quite as easy to spot. How can we find a length field in the data? Well, we bring in some reverse engineering techniques. What if we increase the length of what we insert one at a time? Surely at that point, we're just looking for a field that's going up by 1 each time you see a new record. So we've just inserted those other records now, so ABC, ABCD, and ABCDE, and we can see those over here. Now, we need to look for that incrementing length field. Let's go back to those ASCII codes that I showed you earlier. I didn't pick these characters by accident. I was very deliberate. Take a look for these characters greater than, question mark, and so on and so forth over on the right when we go back. This is the data we inserted. And look, there's some of those characters. We saw them earlier in that ASCII table. They're incrementing one at a time, and they go up as we increase the length of string that we inserted. If we go back to the hex editor view, we can highlight the hexadecimal representations too. We can see incrementing numbers, along with the data we inserted. It's all just there, but in hexadecimal form. So we're fairly sure that we found the length field now. How about we rewrite some binary logs? Now, if we were good people and we were trying to do this, reliably in production all the time for some weird reason, we could import some parts of the Postgres source and do this, nicely, in quotes. But if we wanted to just, hack it together and do it as a one-off, then we could write a regex. So let's write a regex. If we go back to our highlighted view of the text editor, hex editor, we're going to break this first size field. So we're going to break this 3f and replace it with zeros. Doing so is relatively simple, and we ended up writing this script. It's in Ruby, but you could do this in whatever you want. And it has exactly one interesting line of code in it. We are replacing 3f followed by basically the rest of that record. We're using that just to anchor, so we don't want to replace every 3f that exists in this stream. We just want to replace this one. So we run that, go back to our binary log, and success. We have changed 2 bytes of data. But it's an important 2 bytes, because now we get to give this back to a Postgres replica and see what happens. And it turns out that when we do this, and I can do this locally as many times as I want, and have done a lot over the last few days, we have reproduced this error. And we can do so reliably over and over again outside of production. Success, with a caveat. With our newfound ability to reproduce this part of the production outage, we found out that this was not enough to cause our clustering software not to promote a new primary. We had to go looking at other things that we'd observed from production to piece together the rest of the puzzle. And that was an interesting story in itself, and I recommend going off to read about it later. You can grab the link from the slides. So what can we take away from all this? There's a couple of things I hope you got. The first one is, hopefully you learned some cool stuff about databases. Databases and how they work are one of my favorite topics in CS, along with distributed systems. But there's something cooler for me in this story than that, which is debugging unfamiliar layers of a system. Before I ended up involved in this incident, I don't think I'd ever looked at Postgres binary logs on disk. I knew they existed. I'd done like ls on the folder, but I'd never gone and opened one and tried to figure out what was going on in there. I'm also reasonably sure I'd never used a hex editor. And, I got to grips with both things. It was kind of fine. And for me, the real lesson out of this was the reminder that there's no part of the software you run that is magic. That you can understand any layer of the stack you're working with, even if it's normally abstracted away from you and taken for granted. Thank you. Cool. Awkward Discord clapping. So image credits so that I don't get sued, and questions. If any. Oh, text channel. Okay. I will, for the sake of the OBS recording, that will also not work because OBS can't capture desktop on Macs for some reason. So, question from Dictionary: what caused the spurious binary log? So the actual beginning of that incident was that the RAID controller in the primary Postgres instance just gave up on life and just hard crashed, which meant that the OS couldn't read from the disks. That log file was presumably the sort of last semi-successful read from the disk, and it was shipped off to one of the replicas. So yeah, disk array crashed, nasty log file, got replicated. I see typing. It was probably software on the hardware. When we rebooted it, the card was fine. So yeah, even your hardware has too much software in it. why the regex stroke Ruby code to change the binary data? Couldn't you have replaced the relevant byte in the hex editor and saved to disk? Yes, so that's the way I did it the first time. I did it in the hex editor and saved it, but I wanted to be able to, there were 5 or 6 different hypotheses for what caused the actual failure to promote a new replica. And I wanted to be able to test them in different combinations over and over again. And I didn't want to have to edit the file in a hex editor every time I did that. And the file, because it's not quite deterministic what you'll end up with in those files. So you kind of have to, you can't just repeatedly use the same log file. No worries. Does Postgres support writing to multiple replications live-ish and work out in some event sourcing way, or is it always primary and secondary? There are kind of multi-primary things for Postgres. I'd say none of them are like mainline supported, in quotes, but they exist either as extensions or there's some newer stuff with like logical replication that I think you can do that with. It has there's an operator like on conflict merge, which you can use for that stuff. Some more typing. Oh, this is very exciting. It's like anticipation. Did this incident change the way we go about debugging incidents? At a very meta level, I'm not sure it did. Like I think it's probably a few incidents before this that will have done it, but like one of the things that you kind of get battered into as you go further into an SRE career is you aren't allowed to stop diving through layers of like something you're debugging. Like you just have to keep going until you're dealing with like bytes on disk or bytes on a network, even if you were working in like Ruby on Rails to begin with. I don't think this one, for me at least, maybe for other people in the team, but I don't feel like I changed like incident habits from that one. Question, were the 2 other instances I found with grep interesting? Sort of, only in the sense that it shows. So the thing that those two other instances showed me was that Postgres has to handle lots of weird edge cases at the reading stuff off disk layer. So there's other instances, I can't remember exactly which one does which, but I think there was one of them that's kind of dealing with the case where it was only we're getting into one of the rabbit holes now. When you write things to disk, they get aligned to pages, usually 4 kilobyte pages. Postgres has to handle the case where an Xlog record gets split across multiple pages. I think that might have been one of the other 2 instances. So I went with the easy one to reproduce it.